Hey guys, hi. This is Krishna. I'm from BeOne. I lead the advanced analytics, enterprise analytics, and AI side of things at BeOne. And JP, most of you need no introduction to JP. But yeah, JP, if you want to introduce yourself to those newcomers, go ahead.
JP, we helped on this project to identify duplicates in patient-level data, and I believe most of you are familiar with the problem, and we came up with a strategy to identify them, and we've got some results we want to share with you.
Awesome. Thanks, JP. Yeah, so if I remember right, JP came to us probably like a year ago, a little bit more than a year.
Yeah.
It was a long process. And the reason is JP was like, hey, I know you use a lot of claims data, like all of us do. And he was like, there are duplicates in that. And I was like, yeah, there's probably like 5 or 10, maybe 15, 20, like a handful. It couldn't be more than a percentage, right? It's the cost of doing business. Sometimes you buy so much, you get a little bit, dirty data. It is what it is. JP is like, no, it's much more prevalent than that. We see a lot more, and we're able to detect and find it. And would you like to know more about it and try to see if you could, identify those records? So I was like, oh, okay, that sounds interesting. And I took it up the, chain of command, so to speak, and my peers, and they were like, hey, we got a lot of metrics, reports, trends, whatever, right? You guys know the deal. Everything sits on claims. Are you telling us that our foundation is shaky? Like, how big is this problem? is half the data duplicates? Like, everybody's panicking and freaking out. And I was like, hey, no, JP said he's finding duplicates across the board. I don't know how bad it is for our therapeutic area. So let's invest the time, effort, money, resources to figure out how bad it is, right? So that ask, that in itself was really hard to take it up the chain of command and get approval. And then one fine day, we were able to get started on this.
Yes.
So in this presentation, we split it up into two big chunks. I'll start with the problem statement and hand it over to JP, who's going to share how he went about tackling the issue, what are some of the algorithms that he used, define the problem statement, and so on and so forth. And then I'll share insights around what did we glean from this, what are some key findings that we had, and how could you go about doing this with your claims data if you chose to do so. Cool. So let me just get right into it. These are the sections. Again, just reiterating the problem statement, and JP, being JP, gave it a name. You all must have heard about tokenization when you use claims. Maybe you have, maybe you've not. And he's going to go into detail, so I don't want to, steal JP's standard about tokenization, SHA 256 algorithms, and so on and so forth. He's going to jump into it, but he gave it a name. He branded the problem, right, and called it tokenitis, right? Which was, I thought was hella funny. I was like, hey, what's this tokenitis, So it's like, this is problem where tokenization doesn't work as intended. And again, JP is going to go through that. But the problem with that is, like I said, anything and everything that you do at the patient level is going to be based on claims data. And when that foundation is shaky, you're like, is this share number right? Is this NPS number right? Are all my metrics right? How wrong are they? Oh, I saw this thing change this month. Is it right? Is it because of bad tokenization? Did the vendor get a new data source? So on and on and on, right? So how do you get ahead of it? So that's the idea behind doing this. Because when your foundation is not strong, you're going to face a lot of questions. And even if you don't know what the problem is, not knowing the issue, not knowing how bad the issue is, creates more issues, right? I just want to call that out. So without much ado, we'll jump into JP's interesting sections.
Okay, thank you, Krishna. Hello, everyone. So we'll start with, when you look at patient-level data, it's based on the patient ID. And the patient ID means that each time you get a different ID, it means it's a different patient. And each time you see the same patient ID, it means it's the same patient. At least that's the promise, right? And so to kind of shed light on this, let's take a step back and see how the sausage is being manufactured. right? So how do we cook that token? So the token is based on the name of a person, the gender, the address, and the date of birth. So let's look at what that means. It means that if we are able to cook the token very well, it means that the name, we know the name very well, we know the gender very well, the date of birth and the address. And you won't be surprised that actually that's not exactly the case, right? So let me give you a few facts, right, about PII. And the 32% of adults, 1/3 of the country, have changed name legally. So the typical case would be the woman that gets married and changes name, and there are about 20% and 4% of them for other reason. 110 million of people have more than one legal name in the country, right? 80% of the women that marry change, 4 out of 5 change their name. Many would prefer to keep the name or hyphenate the name, right? And another interesting fact is that out of we're about 333 million people, something like this. 120 million people have a unique first name, last name. It means there's no one else that shares that name with you. And which means that 210 million people, if you have that name, there's someone else, at least one person that has the same name as you do, okay? And also we have the transgenders, right? So there will be change in gender and name that accompanies that. And then we have about 36 million people that move every year, right? So over a period of 5 years, looking at PLD, then you can imagine maybe 11, not the times 5, but maybe like times 2, probably the same people moving around all the time. So you can see a little bit that this thing is a little fragile now, right? Given the backdrop of those stats, like first name, so you have the namesake that we know, the women that gets married, the flip between the first name and the last name when it is not very clear which one is the first name, which one's the last name. Not really obvious, right? Gender, date of birth. About 40% of the databases, they don't have the date of birth, they only have the year of birth, right? You're nodding and you know that very well, right? And then the address change, and not all pieces of information are there. Of course, there are typos, misspelling, and all that good stuff. So I'll give you kind of practical pieces of evidence why you should be like St. Thomas, right? You should be doubtful of what's going on. For one client project we did, one vendor, which I'm not going to name, had more patients than the database that tracks every single transaction that happens, 22% more, right? So this is the miracle of Jesus. Health Verity, I don't think Health Verity is here today or in the conference. They published quite a few things about the false positive, false negative. And Health Verity says we have a very, very good system and the industry sucks. And they have up to 42% of false negative, and which kind of sounds on the high side in my mind, meaning that there are different patients that we couldn't combine. And I believe how they got to that number, I think it had to do with, if you take a group of people and you look for the same birthday, right? So if you take 100 people, on average, you'll have 14 to 15 pairs of people that would share birthday with someone else. And if you grab 100 people at random in a database, and you can compare that number, of course, you get the central limit theorem and all that good stuff. So you do it frequently enough, then you can say with some confidence that actually there are too many people that have the same birthday, right? So there would be like duplicates. I'm not sure this is what they do. This is JP talking. I could be completely wrong, but they probably don't have access to the other guys, I would think. So they should have some other techniques like the one I just described. There's a Viva SafeMind. They're going a little different track. So they cook the token not only using the PII, but also the claims. And that allows them to reduce the errors that they have because they can recognize that the names have been flipped or the birthday has been flipped, right? The year, month, year kind of stuff. And they quote numbers like high numbers in the false positive and false negative. We'll read here, kind of high numbers. I'm not endorsing those numbers. I'm just saying that a vendor that is in the business is telling how bad, ugly the other guys are, and those are the numbers, right? And we did some analysis looking at CMS, Medicare data. And we know there are suppression rules when you have, for example, in Part D, if you have less than 10 claims, they won't tell you, they just hide it. If you have less than 10 beneficiaries, they would tell you what it is, and then they would put a little kind of blank and not tell you, kind of, they hide half of it. And what we've done is we look at the data from the vendor, and then we compare it, the Medicare data. And interestingly, after accounting for the suppression rules, and we know we have both the FFS and the managed part, accounting for that, we get the whole caboodle, so to speak. The vendor had more claims and physicians than what CMS says, right? Okay. Another piece of evidence is that some of the vendors have 100 million Medicare patients, right? And we know today is around like 62, 63 million Medicare. And Krishna said, JP, you know, people die a lot when they're older, right? So maybe what's happening is they got the 100 million from the people that are dying if you take like 5 years of data. And so, you know, I said, oh, Krishna, that's a very good comment. And I run a little calculation that I'm showing on the slide here, taking, you know, how many people die. And then we know that Medicare, it's like 89% or 65 plus, like 11% or disability, blah, 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 and Lou Gehrig's and ESOD and so on. Accounting for that stuff, it would mean that the data vendor has complete picture for 14 years in a row. And when you check the PLD data, we know that the FFS is not perfect. So clearly, the only conclusion you can have is they have duplicates. So just to recap, we have Health Verity telling us that we have Crossix showing us that things are not great. On the one that we had was some of the in-office dispensing would report, you know, something like 75% of new patients. We know it has to do with the token, nothing with reality. We talk about Medicare, we have the 100 million. You get the story, right? The evidence is compelling that there are duplicates in the data. I mean, it's happening, right? Okay, very good. So do we have a way to identify the duplicates? There's one thing to say they're duplicates. The second thing is to say this is a duplicate, right? And the big challenge we have is we don't have PII. When we get the data, the PII is gone, right? We don't have PII anymore. So when you look at the disease of token, let's call it tokenitis. So we have 3 forms of tokenitis. The first one, which we're going to look at here, is a tokenitis duplicata. It means that the same patient has multiple patient IDs and their overlap in the claims. The second tokenitis is tokenitis splitica. So one patient gets 2 patient IDs and there's no overlap between their claims. And the third one is tokenitis collisionica, where you have 2 patients that get mapped onto one patient ID, okay? So in maybe next year, I'll tell you about the other cool stuff I have, but today, we're going to talk about duplicates.
I just want to say it's the coolest naming, right? So it's just fun to just, because, it's like data, numbers, it's boring. So, I'm just glad you named it such funny names. So thank you.
So we're going to talk about we call it the magnet algorithm. And that's the algorithm that's going to attract the duplicates that we're going to come together for us, right? So we've done work to merge databases, PLD databases, when they're tokenized differently, right? So you can picture all the major, well, it doesn't have to be major, by the way. Any PLD that you can think, open, closed, we don't care. We can match them. based on the overlap of the claims. So in essence, it has to do with what is the probability that two patients, different patients, they have the same age, they have the same gender, they operate in the same geography. They went to see Dr. John Smith on the 7th of February, and they got those ICD codes. 1 week later, they got the same NDC code stuff, and 2 weeks later, they went to the hospital the same day, got out of the hospital. What is the probability of this happening? We can compute that probability, right? So we computed the probability of those overlapping claims, and then we have some kind of threshold and say, this is most unlikely to be due to fluke, right? Something may be happening there. So we did projects where we combined not 2 data sources, but we combined 4 data sources together. So we created like a dictionary. We have the Bayser ID, and then we have, data source 1, this is how they call the patient, the data source 2, this is how they call the patient, and so on. And for many of them, we don't have all 4 of them, because otherwise, why would you buy 4 data sources, right? You buy to have the increment, right? So for several of them, you have like 2 or 1, and some of them you have 4. And so around April of last year, I get that wonderful idea. And I said to myself, what if we match a database against itself? Right? So the JP, you're really stupid, man. Why would you ever do that? Why would you match it? Because we know there's a patient X that's going to match patient X. That happens in 93% of the cases. In 7% of the cases, patient X matches with X prime, X double prime, X triple prime. And in English, what it means, those are duplicates, right? That's how we identify duplicates without having PII, okay? So now we have different levels of confidence based on what we call the NLP. It's not a great choice for not natural language processing, but it's a negative log probability of this happening. It's like when you compute the pH of solution, it's like negative log probability, right? So we use the NLP as one of them, but then we look at different criteria. And so we can layer the levels of confidence that we have when we say that those guys are duplicates. So that's kind of the essence of how this thing works. And one thing that we need to manage when we do that is that we call it the cross. And basically, when you get the patient X is going to match with the patient X with a certain probability, right? No, you're interested in the negative log, actually, of that probability. But it matches with a given probability, which is a function of the number of claims that overlap, and the rarity of some claims. If you go, it's a physician visit, this is very common, so you can't say too much. But if it is a very specific ICD code, this needs to carry some weight to it, right? So we factor all that, and the NDC code and has to do with the frequency of occurrence of the drugs and the procedures and that stuff. So we can compute what is the kind of the other suitors, if I can use that word, for patient X, right? So there would be a Y or X prime and so on. And that little chart on what you have here captures this. So we analyze this to be able to say, okay, there's a challenger, but the challenger is serious enough that maybe I want to call it a duplicate, right? If it's not too strong, like I think the size of the bubble shows it can give you an idea of how strong it is, then we say, oh, we're not very sure about that. So with that, we'll share some results with you. Krishna?
Thank you. Thanks, JB. All right. So with that, we were like, okay, let's run it on our data and see what happens. But before we started doing that, we set some ground rules as to what do we include at what level. We can't just merge the entire data set with the entire data set. What are some ground rules, right? Do we take into account location, gender, age buckets? So something where we say, hey, yes, PII does take these into account, and then there are typos, yes. But apart from that, let's at least have something to go off of and say, okay, if these things are the same, then let's see what happens with all those transactions. We looked at the data set across RX, BX, DX, and so on and so forth. You guys probably are, fluent in these terms. So we looked at it all and we said, okay, let's see what is happening within our own data set and how bad is this issue. And let's quantify it to JP's like JP just shared, hey, let's do a negative log and see how many such transactions are out there that seemingly two different patients share, right? So let's see how bad the problem is. So when we looked into it, we found hundreds and like literally thousands of patients where we could tell, oh wow, this tells us this patient has so many records across, let's say, RX or DX or PX that are similar. This doesn't make any sense, right? So when we looked at the negative log, we were like, these numbers look suspiciously large. Did we do something weird in our algorithm? Let's triple check. And then we were like, okay, let's just take a couple of examples to see, like, this doesn't make sense. Let's dig in, take two patients to see, like, a couple of examples to see what's going on. So that's what we did next. So when the one on the left shows, hey, two different patients had around 100 or odd transactions from the DX table on the same date with the same HCP over a period of 3 to 4 years. And we were like, this doesn't make sense. I love JP's example when he first shared this with me. It's like going on the freeway and you're sharing the freeway with other cars, right? On the freeway, there'll be cars in front of you, behind you. If there is a car next to you for 5 miles, you're not going to think much of it. It's the freeway. We all got to use it. Once you get off the freeway, you're making a left, you're making a right, you're doing a few turns, and you still see that car behind you. You're like, hey, is this car following me? And then you do 10 other turns and it's still behind you. You're like, oh, whoa, hey, I think there's something going on here, right? What do I do next, right? So that's what we said. Hey, some patients are going to go to see the same doctor on the same day. They live in the same place. They're in the same age group. Your therapeutic area might be like, hey, it's mostly for this age group of patients. So yes, there is some commonality there. But if two patients are having the same, transactions with the same doctor on the same date for years, you're like, whoa, hey, something's fishy here, right? So then we said, okay, we did look at it individually to make sure that, okay, the algorithm was not hallucinating. I know everybody likes to use the word hallucinating, like, what if it hallucinates? This is not a Gen AI algorithm, it's a simple old math algorithm, but then we were like, let's apply it on our data, let's see how bad this is, right? And what we found was, if you look at the duplicates, conservatively, it's around 7%. Net key number that you want to take away is like 7. And if you want to be ultra conservative and say, you know what, we messed up, we missed something, let's cut that 7 by half, it's still 3.5%, right? You could say, oh, hey, 3.57 it's not such a big deal. It is when you're doing LOT, when you're doing patient level analytics, when you're doing so many different things. When you start seeing funny trends, you're like, this doesn't make sense. Why is this patient jumping from 7 different LOTs? I don't get it. This is why. This could be why, right? You never fully know because it's de-identified, right? So key takeaways, we found around, like, give or take 3, like around 7. So this is what we found in our data. Going to the last key takeaways that we had from doing all of this is a good image that Gen AI generated, so I'm not going to take credit for it, but it's a good image where it's garbage in, garbage out, right? Do not assume whatever you're sold is good, right? You want to triple check. A good example is you're going somewhere buying shorts, right? Don't just assume, yeah, the shorts are shorts, everything is going to be good. Put your hand inside the pocket. Maybe the pocket is too short. I don't know, right? Check your stuff, make sure the zips work, right? So that's what we're trying to say. Make sure what you're buying, make sure your data passes muster, make sure it makes sense. To JP's point, just because you have more patient IDs doesn't mean you have more data. It could be data that's a little bit shaky, a little bit fishy, right? So that's the key thing. Okay, so now what do you do with this, right? Before you go have a conversation with your data vendor, with your data strategy team, with whoever, you want to make sure you have irrefutable proof on, like, hey, what about this patient? Let's just take this patient. This patient has 250 records in the DX table that this patient shares from a HCP standpoint, date standpoint, and procedure standpoint. Like, what's going on here? Help me with this. And also, by the way, it's not just for this one patient combination. It's for these 1,000 patient combinations. What do we do here, right? So before you go have the conversation, make sure you do your due diligence, right? And get that data ready before you go there. And the last slide we have is, sometimes you will see that in the RX table, there is nothing that's shared. But a lot of times in the DX table, there'll be a lot of records that this two separate patients share, right? So just want to call it out. With that, we want to end our conversation, our presentation, and then jump into the Q&A session. So again, I want to give JP credit to coming up with the image. I just cleaned it up a little bit with Gen AI. So we'll open it up for Q&A.